quantum computer. Now, what if the very materials you're using to construct it, well, what if they're constantly sabotaging your efforts? We're talking about decoherence, the ultimate enemy of quantum computing, that moment when fragile quantum information just vanishes. But here's the truly radical part. Instead of just trying to manage this fundamental problem, what if we could actually get rid of its root cause entirely? This deep dive is all about exploring a bold, almost science fiction-like proposal: creating a quantum computer in what's called a phonon-free environment.
That's right. Our mission today is to unpack this highly speculative yet incredibly high potential concept. We're going to dive deep into the fundamental physics of how atoms vibrate in materials, how those vibrations, well, how they destroy quantum states, and then explore a truly fascinating idea that might allow us to fundamentally suppress these environmental disturbances right at their source.
So let's set the stage. What exactly is decoherence, and why are solid-state qubits, these tiny supersensitive quantum bits, so vulnerable to it? It sounds like an unavoidable fundamental limit for quantum computers built from solid materials. Is there any way around it, or are we just stuck trying to manage the damage?
Well, decoherence is precisely that, the irreversible loss of quantum information. Think of it like a delicate quantum thought that simply dissipates. And for solid-state qubits, whether we're talking about superconducting circuits or, semiconductor spin qubits, the crystal lattice they sit within is actually a primary culprit. The quantized vibrations of this lattice are what we call phonons. They act like a constant, invisible thermal bath, relentlessly interacting with our qubits and just dissolving their delicate quantum states. What's particularly concerning and a real headache for quantum computing is the potential for something called correlated errors. Imagine a high-energy event, maybe something as mundane as background radiation, hitting your quantum chip. That single event can generate a burst of highly energetic phonons that don't just stay put. They can travel across the entire device, simultaneously disturbing multiple qubits. Now, most quantum error correction codes assume errors are local and uncorrelated,
So these widespread phonon bursts are a critical threat. They undermine the whole error correction strategy.
Exactly. They pose a critical, almost existential threat to building a truly fault-tolerant quantum computer.
That's a huge problem. Current strategies, as you said, try to manage this. We have things like phonon traps that try to absorb or scatter these destructive vibrations. But this deep dive really takes a sledgehammer to the problem. It proposes a far more radical idea: to operate a quantum device in a physical regime where the very concept of a phonon as a well-defined particle simply ceases to exist. It sounds like a bit of a magic trick, doesn't it?
Hey, well, maybe less magic, more fundamental physics.
Okay, so to truly understand how we might silence these phonons, we first need to delve into their very nature. What exactly is a phonon in the first place, and where do these concepts like anharmonicity come in?
That's a great question. So the standard way we describe lattice vibrations starts with what's called the harmonic approximation. This model is pretty simple. It treats the atoms in a crystal as if they're connected by ideal, perfectly linear springs. Think like tiny masses on springs. When you quantize these collective vibrations, you get the phonon. Think of it like a tiny, quantifiable packet of vibrational energy with a specific energy and momentum. This elegant picture works really well for explaining many low-temperature properties of materials. But here's the catch. It's incomplete. The harmonic model predicts that phonons have infinite lifetimes and can travel forever, which simply isn't true in real materials. It can't explain why materials have finite thermal conductivity or why they expand when heated, things we observe all the time.
So if that simple spring model isn't the full picture, what are we missing? What's the next step?
That's where anharmonicity steps in. The first improvement, the quasi-harmonic approximation, acknowledges that atomic distances change with temperature, meaning phonon frequencies themselves depend on the material's volume. But it still assumes those ideal springs for a fixed volume. True anharmonicity comes from much more subtle, higher-order terms in the way atoms interact, what we call the interatomic potential. It's the actual force law between atoms. When atomic vibrations become large, these higher-order terms become really significant. This is the physical origin of phonon-phonon interactions, where phonons actually scatter off one another, they decay, and they can even merge. This is what gives them their finite lifetimes. It quickly turns the simple picture of atoms vibrating into a really complex, many-body problem, way too complicated for our usual simple approaches.
And to tackle such a formidable problem, I imagine you need some pretty sophisticated tools, right? Not just pen and paper calculations.
Absolutely. When these anharmonic effects are strong, our standard mathematical tools like perturbation theory, they just break down. They don't work. We need powerful, non-perturbative computational techniques. We're talking about first principles, molecular dynamics simulations, which directly solve atomic motions using quantum mechanics, and advanced methods like self-consistent phonon theory, including modern stochastic implementations like SSCHA. These are truly indispensable for exploring the physics of what we hope might be a phonon-free computing environment.
This whole concept sounds like it hinges on materials behaving in some really extreme and unusual ways. Can you tell us about structural phase transitions and how they relate to this incredibly bold idea?
They're absolutely central to it. Many continuous structural phase transitions where a material's crystal structure smoothly changes with temperature or pressure are driven by a fascinating phenomenon called a soft mode. A soft mode is a specific type of phonon whose vibrational frequency just plummets. It anomalously decreases as the temperature approaches a critical temperature, TAC. It's like a spring that just gets weaker and weaker as you approach that critical point. For an ideal second-order transition, its frequency is theoretically predicted to vanish completely right at TC. This softening signifies a growing lattice instability. The restoring force for those atomic displacements essentially vanishes.
Okay, here's where it truly gets radical, right?
Like,
When does the phonon stop being a phonon? When does it just dissolve?
that's the key, and it happens in what we call the overdamped limit. As the soft mode frequency plunges towards zero, something remarkable happens. The damping rate, which is the rate at which the phonon's oscillation energy is lost, essentially how quickly its peak broadens out, becomes larger than the oscillation frequency itself. So an OSCI becomes greater than us.
Like trying to make waves in super thick molasses.
Exactly like that. In this limit, the atomic motion fundamentally changes. It's no longer a clear oscillatory wave. It becomes more like a relaxational or diffusive movement, like a particle just slowly pushing its way through a highly viscous fluid. In experiments, you see this dramatic shift. The distinct sharp phonon peak disappears completely. It's replaced by a broad signal that's centered right at zero frequency, which we often call a central peak. This is precisely the point where the phonon quasiparticle picture, which relies on a clear, long-lived oscillation, completely breaks down. A quasiparticle is only useful as concept if its lifetime is long compared to its oscillation period, right? In the overdamped limit, that condition is violated. The phonon ceases to exist as a distinct entity before it can even complete one full oscillation. And it's in this regime where the very concept of a well-defined phonon loses its meaning that the proposed phonon-free environment emerges. The system isn't static, mind you. It's just characterized by these intense, slow, non-oscillatory fluctuations. This transformation of the environment is what we're after.
That's quite a transformation. Okay, before we talk about how a phonon-free environment might actually help with quantum computing, let's quickly recap exactly how phonons cause trouble for different types of qubits. What kinds of specific errors are we trying to avoid here?
Okay, broadly, there are two main types of errors we're always fighting against. First, energy relaxation, or T1 time. This is when a qubit loses energy and falls from an excited state, maybe state 1, down to its ground state 0. And second, dephasing, or T2 time. This is the loss of a definite phase relationship between the qubit's superposition states. You can think of T1 as how long the qubit holds energy, and T2 as how long it remembers its quantum thought. And T2 is always less than or equal to twice the T1 time.
Got it. T1 is energy loss, T2 is loss of the quantum phase information.
Exactly. Now let's look at specific qubit types. For superconducting qubits, like the transmons used in many quantum computers today, the primary decoherence mechanism is called quasi-particle poisoning. High-energy phonons, often generated by background radiation, even cosmic rays hitting the chip, can actually break apart Cooper pairs. Those are the fundamental charge carriers in superconducting materials. These excess quasiparticles then tunnel across the Josephson junction that defines the qubit, causing both T1 relaxation and T2 dephasing. And the really insidious part, a single high-energy phonon burst can affect the entire device.
There's that correlated error problem again.
Right. This causes highly correlated errors, and those are particularly damaging because they completely undermine most quantum error correction schemes, which, as we said, assume errors are isolated or local. We try to counter this with things like those phonon traps you mentioned earlier.
Okay, what about spin qubits?
For semiconductor spin qubits, where we encode information in the electron spin, it's a bit different. Phonons don't directly couple to the spin itself. Instead, the coupling is indirect. It's mediated by something called the spin-orbit interaction, or SOI. Basically, Lattice vibrations subtly modulate the electron's orbital motion, and through this spin-orbit interaction, that translates into a fluctuating magnetic field that can cause the spin to flip, that's T1 relaxation, or cause dephasing, affecting T2. The relaxation rate here, 1 over T1, depends critically on the density of phonons that have the exact same energy as the qubit's energy splitting. It's a resonant process.
Okay, so that's a key difference. Superconducting qubits are hit by a broad range of high-energy
Right,
phonons,
it's an energy threshold problem. Anything above 2 delta, the superconducting gap energy.
whereas spin qubits are sensitive to phonons at a very specific resonant frequency.
Precisely. Which means a successful phonon-free environment needs to somehow fundamentally alter the entire phonon spectral density across a wide range of energies, or at least suppress it heavily at those specific resonant frequencies and above the superconducting gap.
Okay, this brings us to the core proposal. So you'd integrate a qubit right there within a host material, specifically tuned to this overdamped limit of a soft mode. How would this theoretically silence or eliminate phonon-based decoherence? It sounds almost too good to be true, doesn't it?
Well, it's certainly ambitious. The idea is to operate a solid-state qubit inside a material carefully chosen for its continuous structural phase transition at cryogenic temperatures. We then actively tune this material right to its critical point using external parameters, things like pressure, an electric field, or maybe mechanical strain. This process drives the associated soft mode into that overdamped regime we discussed, creating that phonon-free state where the phonon quasiparticle picture just breaks down.
So how would this radical change in the material impact the two qubit types we just discussed? Let's start with superconducting qubits.
Okay, for superconducting qubits, their primary threat is still that quasiparticle poisoning from high-energy phonons. In the overdamped regime, the vibrational spectral weight dramatically redistributes. It's as if energy from higher frequencies is vacuumed up, as you said earlier, and concentrated into that broad central peak near zero frequency. The hypothesis here is that the spectral density of lattice vibrations at energies above the superconducting gap, those high-energy phonons that break Cooper pairs, would be powerfully suppressed. This could intrinsically starve the quasi-particle generation process.
But the lattice isn't perfectly still, right? You mentioned these slow fluctuations.
Exactly. That's the big question. The lattice isn't static. Those large amplitude, non-oscillatory diffusive motions still exist. The crucial question is whether these residual motions can still break Cooper pairs, or what the magnitude of the high-energy tail of the vibrational spectrum truly is, even in this regime. That's something we need to figure out.
Okay, and what about for the spin qubits? They had that resonant frequency problem.
Right. For spin qubits, the problem is resonant energy exchange with phonons at the qubit's operating frequency, usually in the gigahertz range. The transition to the overdamped regime fundamentally alters the phonon density of states in this critical range. Those sharp peaks corresponding to well-defined phonons are smeared out and replaced by a broad, low-frequency continuum. This is where the primary hypothesized benefit comes in, a drastic reduction of single phonon-mediated spin relaxation, so longer T1, because you've essentially eliminated the resonant bath. The phonons at that specific frequency just aren't there in the same way. But, and this is a huge but, here's where it gets truly complex and arguably the biggest challenge to the entire concept, the decoherence trade-off for spin qubits. While we might effectively suppress the T1 processes, the qubit is now immersed in a bath of these slow, large amplitude, and long-range correlated order parameter fluctuation.
Order parameter fluctuation, what are those exactly?
So the order parameter is basically the collective property that defines the material's structural state, like the degree of electric polarization in a ferroelectric material. Right at this critical point, that property isn't stable. It's constantly jiggling and fluctuating in a slow, diffusive way across the material. These very slow, chaotic jiggles can couple to the qubit's energy levels via strain or local electric field, creating a powerful source of low-frequency noise with a specific 1F-like spectrum, or flicker noise. And this type of noise is notoriously effective at causing dephasing. It could lead to a catastrophic collapse at the T2 time. The viability of the entire concept hinges on balancing this extremely delicate trade-off. We're trading one type of noise, high-frequency resonant phonons, for potentially another, much nastier type, low-frequency 1F noise.
That's quite the dilemma, trading potentially better T1 for possibly much worse T2. This whole endeavor sounds like incredibly exotic material science. Are there real-world materials that could actually exhibit this behavior at cryogenic temperatures, or is this still purely theoretical?
Fortunately, there are very promising candidates. The most promising class are materials called quantum pair electrics. Good examples are strontium titanate, often abbreviated SRTO, and potassium cantillate, KTOs. These are really special materials where a ferroelectric structural phase transition, a change in their crystal structure that would normally happen at higher temperatures, is utterly suppressed down to below 0 Kelvin by quantum mechanical fluctuations.
Suppressed below absolute zero, how does that work?
It means the classical transition temperature is negative, effectively. Quantum fluctuations prevent the ordered state from forming even at 0 K unless you push it. This makes them incredibly sensitive and tunable at the very low temperatures where quantum computers operate. They exhibit all the necessary physics. Their lattice dynamics are dominated by a soft transverse optical phonon mode. They're intensely anharmonic even at low temperatures. And crucially, their proximity to this ferroelectric state is highly tunable. You can nudge them towards a quantum critical point where that critical temperature effectively approaches absolute zero by applying strain, pressure, replacing isotopes, like swapping oxygen-16 with oxygen-18 and RTO, or even through chemical doping. And the fact that SRTOs is already a standard high-quality substrate, often used in quantum device fabrication, makes it an ideal testbed. It's a fantastic starting point.
That makes a lot of sense given it's already a known quantity in the field. Are there other candidates besides these quantum paraelectrics that show this kind of behavior, or is this our main shot?
No, the underlying principle can be seen in other families, though they might be less ideal for immediate qubit integration, perhaps. For example, some complex perovskite oxides show similar soft mode behavior, though often at higher temperatures, maybe around 150 Kelvin, which isn't quite cold enough for most qubits. Also, layered and van der Waals materials like tin telluride, SNT, that has a ferroelectric transition around 25 Kelvin in nanowire form offer unique opportunities for tuning phase transitions at the nanoscale. Even some magnetic systems, like the insulating magnet line-off, exhibit quantum phase transitions with associated soft modes that can be tuned right down to absolute 0 Kelvin with a strong transverse magnetic field. So the phenomenon is more widespread than just one class of material, which is encouraging.
Okay, so if we can find these materials and tune them precisely, how would we confirm we've actually reached this desired phonon-free overdamped state? How do you measure something that has supposedly ceased to exist?
That's a critical question, and it requires sophisticated experimental probes. You don't measure nothing, you measure the change. We'd use techniques like inelastic neutron scattering, INS, and inelastic X-ray scattering, IXS. These are really the definitive tools because they directly map the phonon energies and lifetimes. They measure how vibrational energy is distributed in the material as a function of both energy and momentum. They allow us to actually observe the soft mode frequency going down, see the peak broadening out significantly, and ultimately watch its disappearance into that diffuse central peak near zero energy. This unambiguously confirms that we've reached the overdamped regime.
So you see the signature change, not the absence itself.
Exactly. Then we have optical techniques like Raman and hyper-Raman spectroscopy. These are sensitive to lattice vibrations right at the center of the Brillouin zone, sort of the vibrational ground zero. By analyzing the light scattered off the material, we can track the soft mode's frequency and how quickly it's damped, allowing us to identify that crucial crossover point into the overdamped regime. And finally, cryogenic transmission electron microscopy, cryo-TEM, can give us direct, real space images of the crystal structure at low temperatures. This is vital for visualizing how structural domains might form or fluctuate across the phase transition, which is crucial for understanding the homogeneity of our desired critical state. We need the whole thing to be in that state, not just patches.
Okay, so let's pull back for the big picture. This sounds incredibly promising, almost revolutionary. But what are the biggest hurdles? What are the major roadblocks to making this a reality?
You've hit on it. The very phenomenon we seek to exploit, criticality, being at this point of extreme sensitivity, is also its greatest challenge. Systems near a continuous phase transition are exquisitely sensitive to any perturbation. Maintaining a stable, homogeneous critical state across an entire quantum chip, well, that's a monumental engineering challenge. Think about it. Tiny thermal gradients across the chip, strain introduced during the fabrication process, microscopic material defects, or even the fluctuating electromagnetic fields from the qubit control and readout lines themselves. The quantum computer itself could, in effect, destabilize the very environment it relies upon. Defects, for instance, could act as pinning sites, preventing the smooth transition and destroying the desired global critical state, turning our uniform phonon-free zone into a patchy, unusable mess.
So the cure could kill the patient, in a sense.
In a way, yes. But perhaps the most significant unresolved physical question, and the one that keeps condensed matter physicists up at night, is that decoherence trade-off we discussed for spin qubits. Remember, eliminating phonons doesn't mean eliminating all lattice-based decoherence. It replaces a bath of high-frequency, wave-like phonons with a bath of those slow, diffusive, long-range correlated order parameter fluctuations. These very slow, large jiggles can couple to the qubit's energy levels through strain or local electric fields, introducing a powerful source of low-frequency 1F noise. And this type of noise is notoriously detrimental to phase coherence, to that precious T2 time. A comprehensive theoretical model is urgently needed to determine if the substantial gains we might achieve in T1 will be completely negated or even overwhelmed by a precipitous drop in T2. That's the real billion-dollar question.
And beyond the fundamental physics challenges, what about the practicalities? Building these things at scale? Because if it only works perfectly for one qubit in a lab, it's not a quantum computer.
Absolutely. Scalability and manufacturing present formidable obstacles. Controlling a single qubit in such an exquisitely sensitive critical environment is an immense task in itself. Scaling that to thousands or millions of qubits, each requiring a perfectly tuned local environment, that's even harder. Any spatial inhomogeneity in tuning parameters across the chip, a slight variation in strain or electric field could lead to dramatic variations in qubit performance, making a reliable quantum computer impossible. Plus, fabricating high-quality qubits on or within these often complex oxide materials, like STO, while maintaining the pristine quality of the host crystal itself, that will likely require entirely new materials growth and device processing techniques that simply don't exist yet. It's a huge materials engineering hurdle.
Okay, so it's a tough road ahead. What's the roadmap then? What are the next steps for future research if we want to turn this highly speculative but potentially game-changing concept into a tangible reality?
It absolutely requires a concerted, multidisciplinary effort. We need progress on several fronts simultaneously. On the theory and simulation front, we need to develop a full quantum theory of qubit coupling specifically to these critical order parameter fluctuations. We don't have a complete picture there yet. We also need to use large-scale simulations like molecular dynamics and those advanced self-consistent phonon approaches, SSCHA, to actually calculate the noise spectral density of candidate host materials in the overdamped regime, and then use that to predict the actual T1 and T2 times. We need numbers.
So better models, better predictions.
Exactly. Then in material science, the focus has to be on synthesizing incredibly high purity, low defect candidate materials, especially in thin film form, which is what's compatible with chip fabrication. A key goal here is to demonstrate precise and uniform tuning of that critical temperature, TC, in these films using practical methods like epitaxial strain, basically growing the film on a substrate that slightly stretches or compresses it.
Making the materials good enough and controllable enough?
Precisely. And finally, for experimental prototyping, the definitive test, the proof of principle, will be to fabricate a single, highly sensitive qubit on a tunable substrate. Imagine, say, a transmon qubit sitting on a strain-tunable strontium titanate film. By meticulously measuring both T1 and T2 as the substrate is tuned through its critical point, we can directly measure that critical decoherence trade-off. We can see, does T1 get much better? Does T2 crash? Is there a sweet spot where we get a net benefit in overall coherence? That's the real test, and it's going to be a fascinating and likely challenging journey.
Wow. So the proposition of building a quantum computer in a phonon-free environment truly represents a paradigm shift, doesn't it? It's not just an incremental improvement. It's a fundamental change in how we think about approaching solid-state decoherence. By harnessing this extreme anharmonicity near a structural phase transition, we might fundamentally eliminate the phonon quasiparticle itself, silencing a dominant source of noise, particularly those nasty correlated errors that threaten fault-tolerant quantum computing.
And as we've discussed, quantum paraelectrics like strontium titanate are incredibly compelling initial platforms. They possess the necessary tunable, low-temperature critical physics, and crucially, they're already part of the quantum device fabrication landscape. But this high potential reward is absolutely balanced by profound risks. The theoretical challenge lies in fully understanding that decoherence trade-off, where suppressing high-frequency relaxation might introduce powerful low-frequency dephasing. We need to know if we're just swapping one problem for a worse one. And the engineering challenge lies in stabilizing and controlling a macroscopic quantum device right at a point of critical instability. That's asking a lot. Ultimately, this is a long-term, high-risk, and potentially transformative research direction. It sits right at the dynamic intersection of quantum information science, condensed matter physics, and cutting-edge materials engineering. It really pulls together multiple fields.
So, what does this all mean for you listening in? Can humanity truly learn to control these emergent, complex, many-body phenomena of matter for quantum technological advantage? Or will these very same complex phenomena prove to be the ultimate fundamental barrier we just can't overcome? It's a fascinating question for you to mull over as you continue your own deep dive into the mysteries and the potential of the quantum world.